All right, guys, happy Friday. Today is our second day of statistics. We're going to be looking at the shape of data distributions today. All right, so last lesson we just covered mean, median, mode. All right, hopefully that was okay. Any questions, let me know. But today, shape of data distribution. So let's take a look at what we did yesterday. We made this dot plot. So like when we say the shape of the data distribution, well, first of all, here is all of our data, right? So the way it's distributed is kind of like the way it's spread out. So this is not the best shape, but like overall, we could kind of like try to fit a curve to the shape. Like if I had to fit a curve, I might draw something like this. So that would be like the overall shape of the data. So usually the data is going to have like a more distinct shape, and there's three main shapes that I want to talk about today. So first shape is going to look like this. And this looks nice and neat and even, right? And I know I drew like a curve, but there's lots of ways to represent the data. So maybe if I represented it with a bar graph or a histogram, right? Maybe our data looked like this. And this would be the shape of our distribution, right? This nice little curve. Or if it were a dot plot, right, it might look like something like this, right? So again, there's lots of ways to represent your data, but if it looked like a dot plot, it just have the same shape, but just in dot plot form. So this is going to be our first shape. I'm going to call this a symmetrical distribution because it looks symmetrical, right? So symmetrical distribution. And that's when our data is evenly spread out on both sides, and it looks symmetrical. So pretty easy to tell. That one, right? Sometimes our data might look like this. I'm going to do another bar graph, right? And sometimes the data might have more data just like clumped up on the left side, and then it kind of just tails off on the other side, and maybe a tiny bit over there, and then I might be like missing some section of my data, which is fine. Like just maybe I have no data there in that area, and then maybe I might have a little bit more. So this data here has what we call a tail, right? Because if we tried to fit like a nice curve to this data, right, we see we have a tail here. So that is called the tail. And you'll notice the tail is on the right side, and so we're going to call this data skewed right. All right, so when the skew is to the right, we have like trailing data on the right side. All right, and that's all we're going to write for now. We're going to take more notes on this in a second. I just want to give you the general shapes. And so you can probably guess if that's called skewed right, we're also going to have something called skewed left. And that's going to be when, let me draw this a little differently, we have the data clustered mostly on the right side, and the data kind of just trails off. It takes a little longer for it to die off on the left. So maybe it might look like this. And this will be something called skewed left, right? Because if we drew out the general shape of this distribution, it would be something like this, right? Then our tail is on the left side. And so that's called skewed left. So you can kind of think like if we have tails on both sides of our curve or distribution, then that's symmetrical, right? You can also call it two-tailed distribution. Some people called it, but I'm going to call it symmetrical. That's easy to remember, nice and symmetrical. right? If the tail is on the right, it's skewed right. If the tail is on the left, it's skewed left. All right, so let's do some dot plot examples, and let's have this new vocab in mind, and we can name our distributions. Okay, so the first one is pet owners. Students from Great Neck South High School were randomly selected and asked, how many pets do you currently own? And the results are recorded below. All right, so this was nice because the data is already put in order for us. That's not always going to be the case, but in this one we have 1, 2, 3, 4, 5 zeros. So you gotta put 5 dots on zeros. Right, you can do dots like we did in the first lesson. I'm gonna use X's today because I feel like it. And then we got 1, 2, 3, 4, 5, 6, 7 ones. All right, so 1, 2, 3, 4, 5, 6, 7. Again, we're just organizing our data in a visual way. We got 1, 2, 3, 4, 5 twos. So 1, 2, 3, 4, 5. 3 threes. 1, 2, 3. 2 fours. We got a 5. 2 sixes. A 7. An 8. A 9. A 10. And there's this one guy that got 12 pets. All right, so what is the shape of this distribution? Well, we have quite a long tail, as you can tell, on the right. So this is going to be called skewed right. This distribution is skewed right. Right, and for the explanation part, we can just say the tail is on the right side. So without any calculations, what do you think is going to be bigger or greater, the mean or the median, and why? So again, the mean is the average of all the numbers, right? And the median is the middle number when you arrange them from least to greatest. So if you want to think about that, that's a good question to think about. But let's calculate it and let's see which one is bigger. And then we'll discuss why. Right? So let's find the mean. All right, so the mean, we're going to add up all the numbers. Actually, I already did this somewhere. I don't know why I would do this again. Oh man, hold on, let me pause this. All right, sorry about that. So the mean, we're going to add up all these numbers. All right, so we're going to do 0 plus 0 plus 0 plus 0 plus 0 plus 1 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 plus 2 plus 2 plus 2. All right, hopefully you got the idea. We're going to add up all the numbers in our data set, and what I got is 97, and we're going to divide by the number of data entries. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 times 2. Right, we're going to have 30 data points. Right, if you count all the x's, there should also be 30 x's, hopefully. And so there we go. Our mean is 97 over 30. And type to enter a calculator. That's going to be about 3.2. Right? It says to round to the, well, it doesn't say to round, but let's round to the nearest tenth. And if we did, we get around 3.2. All right, so there's our mean. Let's figure out the median. So the median, that's going to be our middle number when we arrange it from least to greatest. So because the data is arranged in this table, we can actually use the table to cross out also, right? Or we can also, again, cross out on the dot plot, however you want to do it. But to try to find a middle number, right, we're going to cross out one number from each end. So I'm going to do it on the dot plot. So cross out a 0 and a 12, all right, 0 and a 10. I'm going to cross out 5 at a time just to save some time. So 1, 2, 3, 4, 5, and cross out 5 from the other side. 1, 2, 3, 4, 5. Right, and I'm always going to start crossing out from the top just to keep it consistent. So 1 here, 1 there, 1 here, 1 there, 1 here, 1 there, 1 and 1, 1 and 1, 1 and 1. Right, and then you'll notice we're down to 2. So our median's obviously going to be 2, but again, I'm crossing 1 from each end. So I'm crossing two at a time, and we actually have 2 dots remaining in the middle, right? So remember, when we take the median and we have 2 numbers left in the middle, you got to take the average of those 2 numbers. So of course, the average of 2 and 2 is 2. So the median is 2, right? And by the way, we could have done that also in the table. So if you cross out 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 from the left, cross out 14 from the right, one from each end. And again, we're left with 2 2s in the middle. That's going to be our median, which is 2. And so I know we did the calculations, but clearly we can see the mean is much higher than the median, right? 3.2 pets on average versus 2 pets for the median. That's a lot bigger. So actually that's step 3, which was to calculate the mean and median. Let's just do the mode 2. The mode number that appears the most highest, that is 1. So why do you think the mean was greater than the median? Well, don't you think it has something to do with this tail, right? We have all of these spread out higher values on the right. So when I take the average, those numbers are going to pull my data to the right. It's going to average it up more, right? But when I find the middle number, it doesn't matter how big the number is. I could have had like a 100 here, someone with 100 pets. Right, when I find a median, I'm still just going to cross it out, and that's not really going to affect the median too much, no matter how big the numbers are, right? So the reason the mean is going to be bigger is because the data is skewed right. And really, that's all you have to say, but I'm going to go a bit more into it for our first time. Right? So because our data is skewed right, we have some higher values. So the higher data values are going to bring up the mean. Are going to bring up the mean. Right? And just think about in general, whenever this is the case, whenever it's skewed right, that's always going to bring up the mean, but it's really not going to affect the median as much. So if you go back to our general shapes over here, whenever this data is skewed right, we can say that the mean is going to be greater than the median. All right? So there was our first example illustrating that fact. All right? Again, skewed right, tail is on the right side. I think I gotta make all right, my tail is fine here. Yeah. So mean is greater than median. What is the range for this data? All right, so I know we did a whole bunch of time on domain and range, right? The range was the set of all y values, right? When we talk about statistics, range is going to have a little different definition, right? The range of our data is going to be equal to the max data value minus the minimum data value. So max minus min. Right, so it's a different definition. It's the same word though. So the range in this case is going to be 12 minus 0. So our data has a range of 12. Right, it's just a single number. It's not 0 to 12. It's just 12. Okay, so that's a new definition, you can say. So make sure you know that. We're going to be doing range all the time. And lastly, is the mean or median a better representation of the typical number of pets owned for this sample? Explain. So our median was 2. So we're saying like the normal number of pets a person at Great Neck South has is 2. Like that's a typical amount. Whereas the mean, it's saying this number, which is 3.2, a little more than 3. Right, so which one do you think is a better representation? Well, I guess it's up for debate. It's kind of objective, or subjective rather, right? But when our data is skewed, we're going to be going with the median as a better representation. And the reason that is because when it's skewed, right, again, we have these, maybe this is an outlier, maybe it's not. Again, we'll talk more about the definition of an outlier later. But we have some more extreme values that are pulling up our data. And that kind of distorts what we would consider typical, usually. So whenever our data is skewed, we're going to go with the median as a better representation. So the median, because the data is skewed right. All right, so let's also add that to our notes here. For skewed right, let's say well, actually just add it in general, right? So the median is a better representation of typical when data is skewed. And you'll see this in real life also. Like when we talk about average annual income in the United States, like 90% of the time, they're not actually talking about average annual income. It's the median income that is used a lot more often. And that's because incomes are skewed. And that's because there's a lot of really, really, really rich people that actually skews the data. All right, so anyway, the mean is a better representation. Let's just add over the mean. Right, we really don't use mode too often. Right, the only real situation where we use the mode to represent what's typical is, again, if we go back to the first day, is when we have something like this where you can't really analyze it quantitatively. Right, like what's your favorite color? You can't say, oh, it's an average of orange and purple. All right, so here's our first example. Save some time in this lesson. I don't want to make the videos too long. I already plotted out all of these x's, but the scenario is 20 students were selected to measure the length of the east hallway. 2 marks were made on the hall's floor, 1 at the front of the hallway, 1 at the end of the hallway, and then we got a bunch of students that measured the distance of, or the length of the hallway. Right, so they're all measuring the same hallway. Why might they get different results? Well, human error. Right, because maybe the meter stick is not perfectly precise. It could be a whole bunch of different reasons. So probably human error is the biggest one, but it could also be like tool precision. Maybe it's not precise enough. So what is the mean length of the east hallway? What is the median length? So the mean, again, we're going to add up all these numbers in that table. All right, guys, make sure you actually try this. All right, a lot of people do make mistakes typing in numbers, so just make sure you're careful, you double check yourself. But for the mean, I was getting 8.56, right? Double check me on that. And for the median, well, let's figure out the median together. I'm going to be using the graph or the dot plot, right? Because over here, our data is not organized from least to greatest. So I'm going to start crossing out over here. I'm going to cross out 1, 2, 3, 4, 5, 6. Then cross out 6 from the other end. 1, 2, 3, 4, 5, 6. One from there, 1 from there, 1 from here, 1 from here, 1 from here, 1 from here. And then I don't want to cross out these last 2 because then I have no data left. So these are my middle 2 values, 8.5 and 8.6. So the median is going to be the average of those 2 numbers. So 8.5 plus 8.6, right? Divide by 2 to get the average. And our median is 8.55. So the mean and the median, they're pretty much exactly the same. And that is because well, this data looks pretty symmetrical to me, right? Like if I had to draw this in, I don't really have a tail on either side. So definitely symmetrical, right? So, and to explain, it just looks symmetrical, I guess you could say, really. Or like there's not really an obvious tail on either the left or the right, or the tails are more or less symmetrical. So if a construction company asks you, how long is this hallway? Well, it's probably going to be around 8 point. Well, let's use the mean or the median, are both fine, because when it's symmetrical, it's about the same. So it's going to go around 8.55 meters. So when it's symmetrical, you can use the mean, and usually the median, though, is going to be pretty close to the mean. So it doesn't really matter, right? So for this case, where it's a symmetrical distribution, our mean is going to be approximately equal to the median, right? And let's take a look at the last example. Again, I already plotted this out. This is going to have a tail on which side? On the left side. So what's the distribution shape? It is skewed left, right? So remember that example I was talking about with a whole bunch of rich people? In real life, household income, it's skewed left as well, because there's a lot, or hold on, sorry, it's skewed right, never mind. Okay, forget that. All right, so anyway, over here, this is skewed left. What's the range? The range is max minus min. Range is equal to 8 minus 0. We have a range of 8 years on the car. Oh, I'm sorry, I didn't read the scenario. These are how old the cars are of 25 teachers at South High School. The results are recorded below. So teachers have owned cars with a range of 8 years. So there's like an 8 years difference between the oldest and newest cars that a teacher owns. What is the mean age of the 25 cars? All right, again, check this calculation, but I'm getting 138 when I added up all the data values over the 25 data points. So 5.52, nearest 10th, that's around 5.5. And let's get the median. Right, so the middle number, I can actually just tell right away, that's going to be at 6, because when I cross out that from the left, I will cross out that from the right side, right? We're going to be left with that 6 in the middle. That is our median. So what accounts for the difference between the mean and the median? Well, in this case, we can see the mean is less than the median, right? And that's because it's skewed left, right? These guys, the tail on the left side is going to bring the mean down. So this is the opposite case of skewed right. So what accounts for the difference? The skew to the left accounts for the difference, or the fact that the distribution is skewed left. So would you use the mean or median as an estimate for the 25, for the age, so the typical age of a car for the 25 car owners? And just like when it was skewed right, we're going to be using the median, because the data is skewed left, right? And when the data is skewed left, it's going to skew or pull the mean also to the left. And when I say to the left, I mean it's going to pull it down, so it's going to be lower, right? So let's just add that last bit in our notes here. So as you could probably predict, based on what we did for skewed right, when it's skewed right, the mean is going to be greater. When it's skewed left, our mean is going to be less than the median. All right, so I'm hoping that makes sense. Again, we got these extra values here, you can say, to the left. That's going to pull the mean down to the left. And also, last bit, which we already wrote, but Again, the median is going to be a better representation over the mean whenever we're looking for something typical when the data is skewed. All right, so that's going to be it for today. Have a good weekend and stay safe, guys. And as always, any questions, let me know. All right, take care. See you guys later.